Okay, time for some rotational or angular kinematics examples. Let's get right into it. First example. Let's say you have an ant that is crawling, oh, this is a little off center, there we go. An ant is crawling around the outside edge of a hula hoop with a radius of 0.35 meters. The ant crawls 0.45 meters around the edge in 7 seconds and moves with a constant speed. So, let's see, here is our hula hoop, not as good a circle as last time. Okay, there's the radius. The ant is crawling around the edge of the hula hoop. Crawls 0.45 meters around the edge in 7 seconds and moves with a constant speed. That's good, okay? Constant speed will always simplify things for us. A, how far has the ant crawled in radians around the outside of the hula hoop? Well, we know how far he crawled in meters, and we know the radius of the hula hoop. We can use the conversion between linear displacement, or distance, in this case distance, and angular displacement, or the angle that he travels through in radians. That equation is the one that's kind of a callback to geometry. S, meaning distance, linear distance, or displacement. In this case, I suppose distance would be appropriate. Equals R times theta. The distance that he crawls is 0.45 meters. The radius of the hula hoop is 0.35 meters. So we're just solving for theta, which should be the angle that he crawls through in radians, okay? So to solve this, we do 0.45 divided by 0.35, divide those two. We end up with theta equals 1.29 radians, and we can abbreviate that rad, okay? Now, does this make sense? Okay, does he crawl a little bit more than 1 radian? Yes. Remember, a radian is the angle that is shown by how far a radius would get you if you were to lay it on the circumference. He crawls a little bit more than 1 radius around the edge, so he crawls more than 1 radian. Makes sense. What is the ant's linear speed? This is simple. Linear speed is v equals d over t. Okay, it's implied that we're looking for average, but I'm not going to bother writing that. The linear distance is 0.45 meters. He does this in 7 seconds. So let's see, 0.45 meters. Okay, ant's crawling at about a normal, probably ant pace, I would assume. 0.45 meters divided by 7 seconds. We end up with 0.064 meters per second for v. Okay, a little bit more than 6 centimeters per second. What is the ant's angular speed? Well, we could probably do this in a couple different ways. If we want to, let's practice using the new variables, okay? Angular speed, since it's constant, since the linear speed is constant, we can assume that the angular speed is going to be constant as well. The angular speed is omega equals delta theta, the angle that he crawls through, divided by the time. 1.29 radians in 7 seconds gives us an angular speed of 0.184, and careful with the units, radians per second. Now, we can check this. How would we check this? Let's do this. We now have the angular speed and the linear speed. We know how those are related. We know that v is equal to r times omega. The linear speed, 0.064 meters per second, equals the radius multiplied by the angular speed, 0.184 radians per second. I should be able to predict what r is by dividing v by omega. And I already know what r is, so hopefully r comes out to be about 0.35. If I do divide these two terms, 0.064 divided by 0.184, I get, and of course there's a little rounding because I rounded earlier, 0.35 meters. Physics works. I'll put a check mark there. Okay? Again, see that these equations are not too difficult to deal with. Okay? The only thing is, and again, I don't have the reference tables in front of me. I don't remember exactly what is given to you on the reference tables, but you should have this stuff in your head anyways. You just have to remember what the symbols are and that they translate very easily from linear to kinematic. Okay, the equations are the same, it's just the symbols that change. Question number 2. A 0.65 meter diameter bike tire that was spinning at a rate of 21.5 radians per second is slowed down to a stop over the course of 10 seconds. Let's label what we know here, okay? We know the time is 10 seconds. Slowed down to a stop, let's see. We do know that it was initially spinning at 21.5 radians per second. I'm going to mark that as omega naught. Slow down to a stop means omega final, or just omega, is 0 radians per second. And the 0.65 meter diameter bike tire, if I divide that by 2, I get 0.325 meters, and that is R. Okay? And that might be important to know going forward. Okay? A says, what is the angular acceleration of the tire as it slows down? Remember, angular acceleration is alpha. In order to solve for alpha, we do know the time and the initial and final angular speeds, so this should be pretty easy. We have in the equation omega equals omega naught plus alpha times t. I know that the final speed, angular speed, is 0. I know that the initial is 21.5 radians per second plus alpha, that's what we're looking for, multiplied by 10 seconds. In order to solve for alpha, I would subtract the 21.5 over to the other side, divide by 10. And I get that alpha is negative 2.15 radians. Now careful, I'm dividing radians per second by seconds. So that's going to be either radians per second or radians per second squared, the units of angular acceleration. Now, someone could say, couldn't you also use this equation? Alpha equals, let's see here, omega minus omega naught, or delta omega over delta t. In other words, the change in omega angular speed over the change in time. Absolutely. As a matter of fact, look at what I did in this equation. The final speed, or angular speed, was 0. I ended up subtracting the 21.5 seconds over the other side. This is really like 0 minus the initial angular speed. That's what would be here, omega minus omega naught. And then I divided by the change in time. These two equations are the exact same thing. They will give you the same answer. Now, through what angle has the bike tire moved during its deceleration while it's slowing down? So I want to know through what angle. That means I want to know, okay, what is the final angle that this gets to, okay? And remember, angles of displacement, angular displacement is given by theta. Let's make the assumption, okay, that, and just to make it very simple on us, let's make the assumption that theta naught is 0 radians. It starts at 0, whatever that means, okay? Makes our job a little bit easier. We now know the acceleration, we know the initial and final velocities, and we know the time. There's a couple different ways we could solve this, but I am going to choose to use this equation right here, okay? Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Very similar to x equals x naught plus v naught t plus 1/2 at squared, okay? Let's say that the initial angular displacement was 0. We're solving for theta. That would be 21.5 radians per second by 10 seconds, plus 1/2 negative 2.15 radians per second squared times 10 seconds squared. 21.5 times 10 is 215. 10 squared times negative 2.15. Oops, did that wrong. 10 times 10 times 2.15 negative, there we go, times 1/2 minus 107.5. As this wheel spins down, it spins through 107.5 radians. Now, if you want to know how many rotations that is, how would we do that? Well, how many radians are there to a rotation? One full rotation would be 2 pi radians. The question doesn't ask for this, but I could do this and say, okay, I'm going to divide this by, in parentheses, 2 pi, and I get, oh, I did that wrong, divided by, in parentheses, 2 times pi. Yeah, that seems about right. About 17, a little over 17 rotations. Okay, just something you could do if you want to. If the bike wheel had been traveling on a flat surface without slipping during this deceleration, how far would it have traveled? This question sounds kind of confusing. All it's asking is how far would this, well, how far has one point on this wheel gone? Because if you know how a bike works, if a bike, let's say a bike tire has a circumference of 1 meter, okay? That means as the wheel goes around one time, the bike must have moved forward 1 meter, okay? So all we're looking for here, S equals R theta, we know how far it traveled, and we know the angle through which the wheel was displaced, and we know the radius of the bike tire. Be careful, don't use 65 or 0.65 meters. Remember, that was the diameter. We need to use the radius. The radius is 0.325 meters multiplied by 107.5 radians. Now, you might notice something here about the units. Is the distance going to be given in meters times radians? No, the distance is just going to be given in meters, okay? And that's kind of weird. Radians is a strange unit. If you multiply it by something else, a lot of times it just kind of like cancels out if you multiply it by a meter. I've never found a good explanation for that. I'm sure there is one. I'm sure someone much smarter than me knows the explanation for that. But I've always thought that's kind of an interesting thing about radians. So 0.325 times 107.5 radians. We get that the bike tire, or the bike tire must have traveled 34.94 meters. That's how far it traveled, or it would have traveled if it had been rolling on a flat surface, until it slowed all the way down from its initial angular speed to 0. Okay, so that's a brief overview of how to use rotational kinematics to solve problems. That is not something that is tested that often, but I did this just so you can get used to some of these variables that you will start to see in the next week or so. I will be back with more videos tomorrow on torque, and until then, have a nice day.